Okay, so we had 9.7 probability. You are going to be finding probability of events. We're going to go through the notes as much as we can. Tomorrow we will, you've got 2 days for review, so if tomorrow we spend the entire day going over today's assignment, that's okay, but you need to try them. Does that make sense? Like, part of probability is trying things and trying to figure them out. So for the last 2 assignments, you were figuring out the number of ways things could happen. So now we can do that with probability. Probability are percents, correct? Nothing is over 100. Nothing is over 1 if you go with a decimal. We have things that will never happen as a 0 and things that will always happen as a 1 or 0% to 100%. Are there many things that are 100% going to happen? No. Okay, there are not very many things that are 100% going to happen. Are there many things that, like, never are going to happen? No. I mean, there are some superficial things, but, but there are not, like, things that if you, what's the probability of that happening? Well, it will happen, okay? Now, is a bird going to turn into a dog? No. Okay, that's never going to happen. But when we talk about like realistic things, it's the probability of never happening is not very high. An experiment is anything happening for which the result is uncertain. Outcome is what the result is. A sample space is a set of all possible outcomes in the experiment. The event is the sub-collection of sample space. So the sample space is rolling a dice 1 through 6. The event is rolling a 2. Make sense? So find the sample space for each of the following. 1 coin is tossed. What's my sample space? Yep, I toss a coin. What is my options? Heads or tails. So my sample space is heads or tails. Okay. What if 2 coins are tossed? So you could get tails, tails. Heads, heads. Heads, heads, tails. Tails, head. What about 3 coins? So we better do systematic now, right? Heads, heads, heads. We got to, let's like do this way. Like, is there another one? Well, yeah, but I mean, is there another one that fits in like this set? Okay. So then we'd have tails, tails, tails. Did we get them all? Okay, so those are the sample spaces, okay? The first part of your assignment will be like, what is the sample space of this happening? Okay, so if I said tossing a coin and rolling a dice. So you'd have heads with 1, 2, 3, 4, 5, 6, right? And you'd have tails with 1, 2, 3, 4, 5, 6. So the first part assignment, not very many problems, but there's a couple that are like, what are the sample space? Okay, probability. How do you find, I'm going to just put it out there. How do you find the percent on your test? But what's in the numerator?
Your points out of order.
Okay, what your points, which you want, right, out of the total. So how do I find probability? What you want divided by the total number of things that can happen. Make sense? So if I go back here, and I ask you, what is the probability of rolling 2 heads? If rolling 2 heads. Throwing 3 coins and getting 2 heads.
2 heads?
2 heads. How many options is that?
3.
3 of them?
3 of 8.
Okay. So the probability is 3/8, right? So actually, I should write this a little different. Probability of 2 heads is 3/8. When you write a probability, you always write P for probability and what you're looking for. And it can be some shorthand. Okay. What is if I have the probability of at least 3 heads or 2 heads? So that's heads is greater than equal to 2. Does that change it?
Yeah.
Because at least 2 includes what?
2 and
2
3.
and 3. So how many is that then?
4.
4? Okay. So it's 4 out of 8 or 1/2. Got it? Okay. So we did an and, we did an or. We did 2 or 3, right? And we added the 2s and the 3s. We added those together. What if I said and? I wouldn't add, I would multiply. Okay? So those are how things are going to go. Remember in the last assignment, there were times we could just list out the number of ways that things could happen, right? There were times we could use multiplication to figure out the ways things could happen. And then there were ones where we had to use combinations or permutations. So you're going to incorporate like all of those things in this lesson. Alex, are you okay? Do you need to go to the office? Okay. Okay. Do you guys need this anymore? Probability of event is the number of ways the event can happen over the number of things that are in this sample space. That's what all these, E stands for event, N stands for the number of ways, and S is sample space. So sample space is everything, event is what you're looking for. What you're looking for divided by everything. And if you think about it like a test percent, it's the same thing. It's what you want those points, right? Divided by how many points are available.
So S is everything.
S is sample. S stands for sample space, which is everything in the sample space. So that's why the first part of the assignment asks you to list different sample spaces. Because they want you to be in that frame of mind. And guys, I will tell you, these problems don't get easier until you just do them and do them and do them, because it's reading and understand what it's asking for. And that's why I said tomorrow, I want you to go through all those things, but tomorrow if we have to be going through a bunch of problems to figure out what they're asking for, that's fine. I just want you to try them beforehand, okay? So make sure you're writing down your work and not just putting it in your calculator and putting your answers in the computer. Okay, am I good? Okay, so we already talked about this. 0 is never going to happen. 1, it is absolutely going to happen. Okay, give me something that is absolutely going to happen.
The bell's gonna ring at 8:15.
What if the bell shut off? Right? Is it have they malfunctioned before? Yeah. So is there a chance that they don't? Yeah. Something else.
The Earth will rotate. She's not gonna stop.
What if it does?
Well, it will in like a billion
Well,
years.
But you don't know that.
Today it will rotate.
You think?
Yes.
How about I will die? Will I die at some point?
Maybe not today.
I didn't say today. Will I die at some point? Yes. Will you all die at some point? I hope we do. I don't want to live forever. That would be horrible. Okay. So there aren't a whole lot of things. Like you're like, well, the Earth will move today. Well, maybe it doesn't. What if some mentally unstable person pushes the button and everybody starts pushing the button and there is no more world?
What button? What button?
What button would cause...
Oh. I'm not here today, Miss Jane.
Okay, but you see what I'm getting at. when we talk about probability, it's like that pessimistic part of you. It's the optimistic and the pessimistic, because you have to think about it like, what if it doesn't happen? Anybody in here do actuary when you did your research career?
Huh?
No, okay. I know one person did. I read it on their thing, but I don't know which class it was in. They did actuary, and actuary is the study of probabilities. It's the study of the probability of things occurring. And so that's what they're always looking for. They're like that pessimistic and that optimistic. It's like, okay, well, I won't die today. Do you really know that? Like, can I 100% say that I will not die today? No. I'm going to step in my car. I'm going to get in my car in an hour and a half, and I could pull out and somebody could hit my car and I could be dead, right? So somebody's like, well, I'm going to wake up tomorrow. Are you?
I don't like the way you think.
Okay. No, what I'm saying is, are there a lot of things 100% going to happen?
No.
No. Now, are there reasonable things that will never happen? Reasonable. Like I said, no bird is going to turn into a dog. That's not even reasonable. So there's not a whole lot of those either. Now, there's a very, very, very slim probability that today we're going to reach 100 degrees. Correct?
Yeah, it's not that slim in Nebraska.
Yeah. In Nebraska, who knows? So, but do you realize today we will be 65 degrees warmer than we were a week ago? That sounds crazy, doesn't it? But it's true. So that probability, can it be really, really small? Yes. But can it be there? Okay. Tossed, 2 coins are tossed. What is the probability that both are heads up? So our combination,
1/4, right?
what?
Like 1/4, isn't it?
Well, we had heads,
Oh, that's true.
heads, heads, tails, tails, heads, tails, tails. Yes, that was the one. Okay, so how many total? Both heads, right? So 2 heads. So
4.
there's 4 total, so that's the denominator. And how many are 2 heads?
1.
1. So it's 1/4. Okay, so some of them you know is 1/4. Like, you'll use this a lot. Okay, a card is drawn from a standard deck of playing cards. How many are on a standard deck? 52. What is the probability that there is an ace? There's 4 out of 52, or probability of an ace, right? So 452, silent, Alex. Or if you think about it, it's 113, because there's how many suits? What? How many suits? There's 4. So 4 suits. So it's 113. So anything.
Oh, my bad.
If you, I think about playing cards in just 13s, because I'm usually talking about a suit, unless I have to talk about it more. But Sam, are you getting more comfortable with cards because you were the one that said you didn't know much about cards? Okay, so most of the problems on the assignment told you what they were, right? Like it talked about a full house. If we would have read the problem and not just went in our head, ask the questions. Okay. 2 6-sided dice are tossed. What is the probability that the total of the 2 dice is 7? So how can I make 7 with 2 dice?
1 and 6, 6 and 1.
1 and 6, 6 and 1, 5 and 2, 2 and 5, 4 and 3, 3 and 4. Okay, so how many is 1, 2, 3, 4, 5? Oh wait, probability sum of 7, right? Oops, that's looking more like a 2. So we have 6, yes? But how many dice do we have? 2. So we have 6 outcomes and 6 outcomes, yes? So it's 6 over 36, or 1/6. And why is it 6 times 6? Because I have what? 2 dice, because it's 6 and 6. So I'm multiplying. Okay. The pick game, a player chooses 6 different numbers, 1 through 44. These 6 numbers match. If the 6 numbers match the ones in drawn in any order, so it doesn't matter the order, the player wins the top prize. What is the probability of winning the top prize of what they buying 1 ticket? So I'm going to draw 1 ticket, and I have to get 6 numbers. What's the probability of me winning this? How many numbers win?
6.
How many numbers win? How many tickets win? 1. Yes? There is 1 ticket that wins this, yes? So my numerator, so we have the probability of a win. My numerator is 1 because there is 1 way to win this. My denominator is going to be my issue. How many different ways can I choose these numbers? What do I use to choose things? Because does the order matter? Nope, so I use combinations, correct? So it's, how many numbers are there? 44. And how many am I choosing? 6. Okay. So, that's the reciprocal, right? Because it's 1 over the choose, so I do the reciprocal. Everyone clear on that? So I have 44 factorial over what? 38 factorial, 6 factorial. And then, so I have 6, 5, 4, 3, 2. 44, 3, 42, 41, 40, 49.
39.
39, I'm going up. And I went up. I went up and I should have gone down. Thank you. 39. And the rest would reduce out?
Yep.
Okay. So anything good? Oh, 5, 4, and 2 get rid of 40, right?
Where's the 38 on the top? The 6.
44 minus 6. Because it's 1 over, so you reciprocate it. Because the formula is n factorial over n minus 1 factorial r factorial. What do you guys want to reduce out? You want to leave the 40 and reduce other things?
Yeah, 40 is easier to work with.
Okay.
There's nothing else you
You
can
can
use.
do 6 and 42, can't you?
Yeah, 6 and 42.
4 and 44.
Yeah, 4 and 44.
3 and 39. 5 and 40.
So we might as well just do the 10 and the 40 and make it 4.
Yeah.
Okay. Really didn't make anything a whole lot easier, did I? Okay. If you guys...
Go into?
What?
What did the 3 go into?
The 39.
Oh, okay.
Because I took, 13. If you guys take your calculator out, your good calculator, you do have choose on there.
I've seen that.
I do expect you to set it up, I do expect you to show me this. Got it? Okay, so you can put in there 1 over 1 divided by, and then go to math, probability. Oh, you guys have to do something different. You go to math, probability. Okay, 1 divided by, go back, sorry. Okay, so, and then 44, for 44, go math, probability, and go down to choose. And hit enter.
NCR, right?
And then 6. And you just
Wait,
fill
what
yours
am I?
in. Yeah,
I'm confused.
and then just fill yours in. Oh, you do it, yeah. Yeah. You guys with those calculators are different.
They gave me one of these. 1.4166.
Yeah, because we're going to have a percentage, yes? Now, if I want a fraction, it gives you point what?
1.416620.
1.
1.4166. Yes.
Should not be 1. That number should be less than 1. E to the negative 7.
Yeah. Oh.
Okay, no, that's
Yeah.
exponential notation. So 1.7 what?
1.416620.
Okay, we don't, just give me 3.
1.416.
416.
Yeah.
Okay, times 10 to the negative 7. So that is 6 zeros, yes? So 0.12345611416. Okay, is that a good chance of winning? No, that is not a good chance of winning. Now, on that, hit math. Don't be on that answer. Hit math. And then fraction.
It doesn't work.
It won't put it in a fraction?
No.
And hit enter. Okay. Sometimes you can always check and put it into a fraction. Sometimes it will do it, sometimes it won't. That fraction's really, really small, right? So it won't put it in a fraction. If you wanted it in a fraction, it'd be 1 over, go ahead and do 11 times 43 times 7 times 41 times 4 times 13 and tell me what that number is. Just list it, don't, just say the numbers, not, the actual amount. Does that make sense what I'm saying?
705905 2.
2? Okay, so is that really, really small?
Mm-hmm.
Yeah. And all we did was, because the numerator reduced all to 1, right? And we just multiplied those out. So we know the probability of winning the lottery is very slim, don't we? And that's just an Arizona game. So what do you think the probability of me winning a national game is? Yeah. Okay. So one time I had a class, they're like, I'm going to win it once and then I'm going to buy all those tickets. Okay, so you're going to buy, if you do, this is 44 choose 6 is 7,059,052 tickets. So you're going to buy that many. Okay, so I don't even play the lottery, but I think they do it twice a week. They draw it twice a week. Do you think you even have enough time to buy 7,059,052 tickets between drawings? No, not unless you made the list of 7,059,052 different numbers. Then you split it up between people and said, go in those convenience stores and buy those tickets. And what is the probability of getting every single ticket exactly right? Well, especially when you go in with 100 tickets to buy. Do you think that person's going to get very, maniacal about putting them in? No, they're just going to start typing in numbers, right? So I don't think that's a good scheme. They thought that was a good career plan to just win the lottery and then buy that many tickets and then win the lottery again. I don't think that works that way. But I don't know. So now, probability of the union of two events. We've used union before when we've talked about if you're using interval notation for domains, you've had to use a U, yes? It means together. So if A and B are events in the same sample space, the probability of A or B or is add. Got it? Mm-hmm. Or is add. Now, the reason why it says probability of A plus the probability of B minus, this is the intersection between the two. I'm going to give you an example of that. So if I do this is A and this is B, do they overlap? Okay, so aren't the things in here counted twice? So that's why you take it out once. You only count it one time. Make sense? So these are not exclusive. These are not exclusive. But if they're mutually exclusive, that means A and B have what in common? Nothing. Okay? So, okay, mutually exclusive. What's the probability of drawing a name in this room and getting a male or a female? Is that going to happen both at the same time? No, you were male or you were female, and that is it. Okay, but what is the probability of getting a male or a junior? Can you be a male junior?
Yes.
Yes. So you would take the male plus the junior and subtract what they have in common. This is done a lot on your own, just in your head. Like if I gave you a table of numbers, you would just add what you needed. Okay. Again, mutually exclusive means they have nothing in common. The Venn diagrams make that kind of show that better than anything else. Alex, are you going to write that down, or are you just going to wait till later? Watch it. You're going to write this down?
What part?
Well, the mutually exclusive and then not. Again, mutually exclusive means nothing in common. Exclusive means you're they neither one have anything in common.
I love the words mutually exclusive.
What?
I love the words mutually exclusive. I use them in every essay I've ever written.
Oh, really? As long as you're using them right. Long time ago, they had the Nebraska State Standard Test, and when we gave it, I can't answer anything. Every year, the kid would say, "What does mutually exclusive mean?" Every year, I'm like, just say the word. Like,
I know a lot of people confuse exclusive and inclusive. I don't really know why, but
I don't know. Inclusive means together.
And it writes on the bottom part.
As long as you know what mutually exclusive means. You've got mutually exclusive here, don't you?
Mm-hmm.
And you've got your picture, so you should know they have nothing in common.
Okay.
Kyan, are you good?
Yeah.
Okay, just one card is selected from a standard deck of 52 cards. What is the probability that the card is either a heart or a face card? Okay, what's a face card, guys? A card that has a what on it?
okay.
A face. So, probability of a heart or a face. Yes? So, we're going to add these. Okay? And then we're going to take away what they have in common. Okay, so how many hearts? What's the probability of picking a heart? 13 over 52. Okay. What is the probability of getting a face card?
13.
No.
Or no.
There's Jack, King, Queen, yes.
3 out of each.
3 in each suit, so that'd be 12 out of 52. So how many heart face cards are there? 3. So I subtract 3 out of 52. Now, could I write this as 13 plus 12 minus 3 over 52? Oops, not 55.
You could have missed one because it's the same job.
Right. They all have the same denominator, yes? When they have the same denominator, I usually write it like that just because it's easier to look at from my brain. Okay, so what, 22 over 52? So 11 over 26?
Yeah.
Huh. So what if how could I write this problem and get mutually exclusive events with that cards. How could I write a card problem mutually exclusively? Doesn't have just cards. It doesn't have to be with face cards or whatever.
You could do hearts and spades.
Hearts and spades. If I asked how many, like, probability of getting a 2 of heart or a 5 of spades, are those have anything in common? No, they have nothing in common. Even if I had a 2 of hearts and a 2 of spades, they still have nothing in common, right? It's a 2 of heart or a 2 of spade. So it'd be 2 over 13. Because there's one of each. Okay. The personnel department of a company has compiled data on the number of employees who have been in a company for various period of time. The results are shown on the table below. Okay, if nothing else, you should know you're going to have to read. Okay, a lot. And you're going to have to reread. Never, ever do a problem reading it only one time. I read it, I write down what I think it's asking me, and I read it again to make sure that's what it's asking me. Because you all know that when you read stuff, you kind of decide what it's going to ask you about halfway in the middle. And we don't always read exactly what it's asking for. Okay, if an employee is chosen at random, what is the probability that the employee has 4 or fewer years of service? 157 out of what?
All of those.
So what should you be doing right now? Adding all that up? $592. Okay. Now, if I need to reduce that, easiest way to do it, since you have a calculator in your possession, put in there 157 divided by 592, hit math fraction, and it will reduce it if it can be reduced.
I got 529.
Yeah, me too.
Okay,
Oh,
then.
That's what I meant. Sorry. It says that. I just looked on the numbers.
Okay. Anyway. Does 157 over 529 reduce?
No.
I don't think it does.
I
But,
don't think it was done
no. Okay. The only thing it could be like, it could be some like 7, 17, something like that with the 7 and the 9, right? I added them up and they aren't divisible by 9 or 3 and they're not even, so. Okay. Next, 9 or fewer years of service. So probability of less than or equal to 9. Yes? See how you can do shorthand? Okay, so what would you do there?
246 over 529.
Where'd you get 246?
89 plus 157.
So 157 plus 89 over the total. So you get 246, and you should check and see if it reduces. I don't think it does either. It might. No. Okay. Okay, independent events. 2 events are independent if they have no effect on one another. If A and B are independent events and the probability of both A and B will occur, probability of A and B. Or we added, yes, and we multiply. So we take probability of A and probability of B. This is the one you tend to do naturally because you have done it before. So you might want to write that down. It's in a box. Just probability of A and B is probability of A times probability of B. What if I said probability of A, B, and C? Then you would multiply all of them. Does that extend? Yes. Does it extend on the mutually exclusive also? Yes. General rule of thumb, and multiply or add. In general. But not always. Got to read between the lines a lot. Good?
Yeah.
Random number generator on a computer selects 3 integers 1 to 20. What is the probability that all 3 integers are less than or equal to 5? Okay, probability of less than or equal to 5. All of them. So I generate one number. What's my probability? Oops. How many numbers are less than equal to 5? 5. How many numbers are there in total? 20. Okay, so that's one time. How many times am I doing this? 3. That's once. So I got to do it again, don't I? Yep. So then it's 5 over 20. And then it's, what again? 5 over 20. So 1/4 times 1/4 times 1/4. And 4 cubed is 64. How could I change that problem and still be multiplying?
Less than or equal to. Oh, you can change it to a different amount of numbers.
Yeah. Or could I say non-repeating?
Yeah.
So if it was non-repeating, how would that change?
It would be 5, 4, 3.
So less than 5, no repeats. It would be 5, 4, 3. But what would your denominator be? How many numbers would I have the first time to choose from?
20.
20. But how many would be the second time?
18.
And then
18.
18. So can it affect both the numerator and the denominator? Okay. So this would be gone, right? So 3, what's 19 times 18? Oh, wait, nope. 19 times 6, right? So that would be 4, 5, 214. My alarm did not go off. I'm sorry. Okay,